Today we're continuing our discussion of the Schrodinger wave equation and electron orbitals. We were discussing yesterday about the magnetic quantum number m sub L, which is the third quantum number. We have n, we have L, we have m sub L, m sub s. The n is the principal quantum number and usually describes the size of the atom, the size of the the orbital, and usually has the value of an integer, 1, 2, 3, and so on. L is less than or equal to n minus 1. So if n equals 3, for example, the value of L can be 2, 1, or 0. M sub L, this is called the azimuthal quantum number. This gives you the shape of the orbital. M sub L gives you the orientation of the orbital. Yesterday we mentioned the p orbitals. The p orbitals can be px, px, py, pz. And the values of m sub L can be plus or minus the value of L. So if L is 2, 1, or 0, m sub L can be minus 2, minus 1, 0, 1, or 2. That gives rise to 5 orbitals, 5 different orbitals, which we call d orbitals. And I've drawn them here to show you what the different shapes are. The dx squared minus y squared orbital is 2 lemniscates that are on the x and y axes. The dz squared orbital is a lemniscate on the z axis with a toroidal shape around it, so it's like a donut shape around a dumbbell shape. The dxy orbital occupies the position between the x and y orbital plane, or coordinate plane, sorry, and the dxz occupies the spaces between the dx and dz coordinate plane, and finally dyz as well. So those 5 different shapes, when you combine them all together, it creates a spherical shape, roughly spherical shape. And if we go to the f orbitals, we get 7 different orbitals, because with f, what we have is a principal quantum number of at least 4, therefore L can be 3, 2, 1, or 0. M sub L can be minus 3 all the way up to positive 3. That gives you 7 different possibilities. And since m sub s can be plus or minus 1, this represents the spin of the electrons. Then you get up to 14 electrons in f orbitals. Now the orbitals have characteristic shapes that represent areas of high probability of finding an electron. And when the orbitals are combined, they form spherical shapes, and it stands to reason that they would all occupy different areas within a spherical area, a volume, because the electrons don't like to be in the same spot. They will avoid each other in space if they can, because they're electrostatically charged particles. They avoid being in the same area. They repel each other. When we think about filling electron shells, there are 3 principles that have to be kept in mind. One is called the Powell exclusion principle, the second is called Hund's rule, and the third is the Aufbau principle. Let's talk about the Aufbau principle. Electrons will fill lower energy levels and sublevels before moving to a higher energy level. All that means is that the atom will fill with electrons. As the electrons pile in, though, they go to the lowest energy level that's available. They won't suddenly go to a higher energy level, leaving a gap of unfilled orbitals. The electrons will always fall to the lowest energy they can find. The Powell exclusion principle states that no 2 electrons will have identical quantum numbers within the same atom. So all 4 of these numbers have to be different for any 2 electrons within one atom. Hund's rule states that when orbitals of equal energy are available, the electron configuration of lowest energy has the maximum number of unpaired electrons with parallel spins. So it's another way of saying that the electrons avoid spin pairing until it is absolutely necessary. And this rule sometimes gives rise to exceptions to the shell filling rules that we have here. This is a mnemonic you can use to help us remember how the electrons pile into an atom. And the way you do it is you write the numbers 1 to 8. Of course, there's no 8. There is no 8s shell, but I just included it because it makes a ramp-like pattern that's easier to remember. If there were 8 electrons, 8s electrons, we would have an element over here under Francium. That would be 8s1, this would be 8s2. So you draw the numbers 1 through 8, put s next to each one, then you draw the numbers, you take off the 1 and the 8, and you draw the numbers 2 to 7, so that these two are have nothing there. Then you take away 2 and 7 and draw the numbers 3 to 6, again put to one side, then you take off the 3 and the 6, and you write 4 and 5. That's your pattern. The first tier has S's, the second has P's, the third has D's, and the last has F's. And the electron shells fill according to this order. You follow the arrows, and that's how the electron shells fill in an atom typically. Each shell has the maximum number of electrons that it will admit. S shells can hold up to 2 electrons, P shells can hold up to 6, D shells can hold up to 10, and the F shell can hold up to 14. And as an example of Hund's rule, because the shells get closer and closer together in energies, it sometimes happens that one half-filled shell can be more stable of an arrangement than a filled shell. And I'll show you an example of that on the next board. Orbitals fill according to the pattern described in the shell filling mnemonic. However, there are some exceptions. An atom having a half-filled or a filled sublevel is slightly more stable, or less reactive, you could say, than an atom without a filled or half-filled sublevel. In the case of chromium, which has 24 protons, the predicted pattern, according to the pattern I just drew on the board, on the second board, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. What's actually observed in the chromium atom, however, is everything the same up to 3p6, but what happens is 4s stays half filled and an electron goes to the 3d5 shell. And the reason that happens is because these shells are close enough in energies so that the spin pairing of another electron for it to go into the s shell would be of a higher energy than it for simply to go to the d shell, where it doesn't have to spin pair. And there are 5 orbitals, there are 5 d orbitals available, so that 5th orbital can hold that 5th electron. So all those electrons prefer to be non-spin paired and in their own shell. The same thing happens with copper. You would predict the following pattern for copper. Copper ends at 4s2, 3d9, but what is actually observed is that copper is 4s1, 3d10. So it's got one filled shell and one half-filled shell, which is more stable than 4s2, 3d9. And the reason that probably happens is because, again, the spin pairing, the energy required to spin pair is higher than the energy that would be spent in simply putting that extra electron unpaired into a d shell that's available and empty.